Just over 100 years ago, Einstein showed how gravity could be imagined as a distortion of space-time. His equations revealed that an object small enough and massive enough could hide behind an event horizon, a point where gravity is so strong that not even light could escape. Astronomers now believe that these objects, known as black holes, exist. They inhabit the centers of almost all galaxies, where they can grow to be millions or billions of times the mass of our Sun. Despite this history and growing astronomical evidence, we have never actually seen a black hole. The Event Horizon Telescope, or EHT, is the first experiment designed to capture a black hole's image. In doing so, the EHT will test Einstein's theory of gravity at one of the most extreme places in the universe, the event horizon. The best chance we have of taking a picture of an event horizon is the supermassive black hole at the center of our own Milky Way. Though it is 4 million times as massive as our Sun, it is so far away that mapping its event horizon is equivalent to standing in New York and counting the individual dimples on a golf ball in Los Angeles. Gas falling towards this black hole heats up to billions of degrees, causing the event horizon to appear as a silhouette whose size and shape are predicted by Einstein's theory. It is best to observe this silhouette in light with a wavelength of about 1 millimeter, where the gas glows most brightly, and light can travel unimpeded from the center of the galaxy to telescopes on Earth. Close to the black hole, the light waves appear circular, like ripples in a pond. But by the time they reach Earth, they are essentially plane waves. Imaging a black hole at this wavelength requires a telescope as big as our planet. The EHT uses a global network of dishes to simulate a telescope of this size. Each dish collects and records radio waves coming from near the black hole. The data are then combined to create the image of the event horizon. This will only work, however, if the dishes are completely synchronized. To understand this, let's use the analogy of a mirror, such as in optical telescopes used for stargazing. Imagine the EHT formed from all the different array sites as one big parabolic mirror. The mirror is curved so that when a line of waves comes into the dish, they bounce off at specific angles and arrive at the focus at the same time. When the EHT sites are synchronized, their recordings can later be perfectly aligned in the same way that the mirror aligns the optical light. If the surface of the mirror is not stable, if it is vibrating, for example, the reflected light rays will not combine properly at the focus. For the EHT, an unstable mirror surface is analogous to an unstable recording. To ensure stability, the EHT uses atomic clocks that would lose only 1 second every 100 million years. The amount of data recorded during observations is so large that it could never be transferred over the internet. Instead, the recordings are stored on hard disks and shipped back to a central facility for processing. There, a supercomputer combines the data from all the sites, staggering them during playback to account for the time difference between waves getting to each telescope. The resulting data can then be used to make images with extreme magnifying power. As more dishes join the EHT, and the more widely spaced they are, the sharper our image of the event horizon will be. In April 2017, the EHT coordinated observations of the Milky Way's central black hole using a global network of telescopes. An international team of astronomers is analyzing the data, eager to bring a black hole into focus for the first time. The results could transform our understanding of black holes, gravity, and even the universe.